In the last episode, we looked at a couple of systems that compute 3n+1. One was the colored marble system of Lisbeth de Mol. We also looked at a string rewriting system using base 6. Are there other types of simple devices that compute 3n+1? In this episode, we'll look at a cellular automaton that computes 3n+1. First, let's visualize a 3n+1 sequence top to bottom with a row for every iteration. Here we start with 7, then get 11, 17, 26, 13, and so on. Every digit has its own color. 1s are in blue, 7s are in orange, like that. Now, let's take a 20-digit number, much bigger, and here are the first few iterations. The start number on the first row is this huge odd number, so we multiply it by 3, add 1, and divide by 2. And when we do this, you can see the iterations are already resulting in smaller and smaller numbers. And we know this sequence is going to wind up at 1 because every number up to 23 digits has already been checked by mathematicians. For the rest of this episode, let's just use the colors. I'm going to drop the digits because they're too small anyway. Okay, what if we try a bigger number, one that's never been tried before, like this random 200-digit number on the very first row here. So every colored box is a digit, 0 through 9. Let's see what happens. Maybe it'll get stuck in a loop, or maybe it'll zoom off to infinity. Let's see. Nope, just goes to 1 like every other number that's ever been tried. How about we start with a really odd number, like 2 to the 400th minus 1? Well, instead of shrinking, this sequence involves bigger and bigger numbers with more and more digits until, nope, it also goes to 1. But these charts are pretty interesting. Look where we get these little columns of zeros in white and 9s in red. There's something about the 3n+1 operations that create those little columns. In these pictures, each row is a function of the previous row. So if this row is an odd number n, then the next row will be 3n+1 over 2. But 3n+1 over 2 is a complicated function because multiplying by 3 involves a lot of carrying. 7 times 3 is 1, carry the 2, like that. So the digit in this box might depend on the digit in this box in the previous row. People have simplified this with a carefully designed cellular automaton. So let's write the start number at the top here in base 6. So the orange block represents the digit 1, red's 2, blue is 3, and so on. So the start number written in base 6 is 7 because there's 1, 6, and 1, 1. So 1 plus 6 is 7. To make the next row, each block is only a function of the block right above it and its immediate left neighbor. So there's 7 possible colors above you, 7 possible colors to the left, for a total of 49 possible conditions. And here are 10 of them that tell you what to put in the next row. So, for example, we look up the pattern white-orange. It says to put a white block under it. Then we look up orange-orange. It says to put blue. Orange-white, put pink. White-white, put white. So we've created the second row. What number did we get? Let's see, there's 3 6s, that's 18, plus 4, that's 22. And 22 is 3 times 7 plus 1. So it computes the 3n+1 so far. And we can do the same thing to create the third row. White, blue makes orange, blue, pink makes brown, and so on. If we create row after row like this, we're going to finally reach a row with 1 yellow block. So if we give this automaton the number 7, it computes 22, 11, 34, 17, and so on, down to 1. And we can run this same automaton on some giant 200-digit number, and it'll very efficiently compute 3n+1 on that. So does this automaton always reach a single yellow cell, no matter what the initial configuration is? Well, that's the same question as the 3n+1 conjecture. So this is another way to think about the conjecture. Instead of thinking about integers and their divisibility properties, we could decide to think about colored blocks and how they evolve over time, or colored marbles and how they evolve over time. Okay, see you next time.